Hello, my sweet students. I'm so sorry I can't be there with you in person today. Please know that I'm thinking of you and I will be back as soon as I can. We're going to start off today by finishing up what we discussed last Friday. So last Friday, you got to play with these fan-powered carts and learn a little bit more about their motion. Now, just to recap where we have already been. Earlier last week, we talked about constant velocity. That says motion. My face is blocking it off. Sorry. All right. But we talked about constant velocity motion. We played with those battery-powered cars that maintained a constant speed and a constant velocity. And when we created a displacement versus time graph for those, we saw a linear relationship, as you see here. All right. So we've got that. And from that linear relationship, then, we discovered a couple of things. We got this new formula where our equation of best fit essentially gave us the formula displacement equals velocity times time, because the best fit constant from Desmos, that A value, was equivalent to the velocity of the vehicle. So there was some significance to that A value, all right? And then from this linear relationship, we also see proportionality between time and displacement for an object that's moving at a constant velocity, all right? So if we double the amount of time that our car is moving, then the displacement doubles as well. If the time triples, the displacement triples. If we cut the time in half, the displacement halves as well. Nice and straightforward when we are moving at constant velocity. But then on Friday, I threw, not literally, but I threw these fan-powered vehicles at you, these fan-powered carts moving along the tracks, which did not move at a constant speed. They were speeding up as they were going. And so we no longer see this linear relationship between displacement and time because the velocity is constantly changing. Now, I asked you last time to collect your data, to graph your data, to ask Desmos to calculate your line of best fit. If you have not already done that, that's the first thing you're going to need to do before you're able to proceed with the rest of the investigation today. I think everyone got there, but if you didn't, if I missed you somehow, make sure to pull out a Chromebook and do that today. All right. Now, if you have graphed your data, applied your line of best fit, you probably saw that a linear pattern doesn't really work anymore. Instead, what we end up with is something that looks kind of like this, where it's curving upward. We no longer have that constant slope. The slope is actually getting steeper over time. So then the question is, what should we call this pattern? Whenever I ask this question, I always get some people who are very excited to tell me that this is an exponential pattern, that we're seeing exponential growth here in this. But here's the thing. For it to be exponential, our equation of best fit would have to take the form of displacement equals something raised to the t power, to the power of time, all right? Our x variable would have to be in the exponent. And that's not what your equation of best fit looks like, all right? So exponential is not it. And in fact, exponential, spoiler alert, will never be the answer in this class. In physics, we are not going to be dealing with any exponential functions this year. So please eradicate exponential from your vocabulary, just at least in the context of physics for now. Your math teacher may still want you to use that, but for this class, no exponential functions. However, what we do see is that we've got time getting squared in our equation of best fit, which means that we are making a parabola here. And so we call that function a quadratic function, okay? So exponential, no. Quadratic, yes, all right? So then a little bit more on quadratic relationships, all right? So we see the shape of the graph here, and we're seeing that there's still a positive slope, as we saw in linear patterns, but now the slope isn't constant, it's getting steeper over time. That's one of those hallmarks of our quadratic relationships. Our equation of best fit takes this form of our y variable is equal to some constant times our x variable squared. And the square is really, really key, and that's that defining feature for this quadratic relationship, okay? Now, we can't use the straight proportional reasoning that we did for linear relationships anymore, but we still can use this pattern to make predictions about how changing time changes displacement. So if we look at this general form of the equation, we see that our y variable, our dependent variable, is proportional to our x variable squared, all right? So what that ends up meaning is that whatever factor we change our x variable by, we change our y variable by that factor squared. That was a whole lot of words. So just to give you a few examples down here at the bottom of the screen, all right? If I were to take my independent variable, my x variable, and double it, the effect on my y variable would be that it would get multiplied by 2 squared, all right? So if I double my independent variable, my dependent variable quadruples, okay? Or if I were to multiply my independent variable by 3, the dependent variable changes and multiplies by 3 squared, all right? Or if I multiply my independent variable by 1/2, we multiply the dependent by 1/2 squared, also known as 1/4, all right? So we get this kind of square proportional reasoning where we sort of have to keep track of which is the independent variable, which is the dependent variable, and then whatever factor our independent variable is changing by, we're going to square that to figure out the effect on the dependent variable. Okay, so that's quadratic relationships in general. Now connecting that over then to our particular lab with the fan-powered carts then, what we're seeing is quadratic relationships played out in the form of accelerated motion, okay? So for an accelerating object like our fan-powered cart, we see a quadratic relationship between displacement and time, which means that our equation of best fit gives us this relationship of displacement is equal to some constant calculated by Desmos times time squared, all right? Now let's go back to that idea of that square proportional reasoning here. So a reminder, time is considered our independent variable because it's on the x-axis. Displacement is our dependent variable because it's on the y-axis. So coming back to that, let's take a moment to discuss with your group, how do you expect displacement to change if you're changing time by either doubling it, tripling it, or halving it? Okay, so basically what's going to go at the end of each of these statements at the bottom of the screen. Take a moment to discuss. All right, so as a reminder, whatever factor our time changes by, we square it to find the effect on displacement. So if my time multiplies by 2, displacement multiplies by 2 squared, all right? So it quadruples. If I triple the time, multiply it by 3, then I'm going to multiply displacement by 3 squared. I'm going to non-hoople it or whatever. And if my time changes by a factor of 1/2, then my displacement will change by a factor of 1/2 squared, or in other words, it will quarter. All right. So this is sort of a starting point for us to start to see this relationship between time and displacement. Now what I want to do is focus in a little bit more on this constant that was calculated by Desmos for you. All right. Now, what you'll find if you compare with other people is just like with the cars, I kind of like messed with things a little bit, and there was a difference between the red carts and the blue carts. And more specifically, the red carts had a higher A value in their equation of best fit than did the blue carts. All right, take a moment with your group to discuss what's the significance of that. If our red cart has a higher A value, what does that tell me about the red cart? All right. So the A value kind of gives us a sense of how steeply and how rapidly our graph is moving upward, right? So higher A value means that we're dealing with a really skinny kind of parabola, something that shoots up really quickly, whereas lower A value, like we saw in our blue cart, kind of slopes up more gradually here. This also tells us something about the rate at which our carts are speeding up. All right, so those of you who had a red cart probably dealt with, like, it got moving so fast that the fan was getting knocked off at the end and all of that. The blue carts just never quite got that fast, okay, because they weren't really speeding up at the same rate. Okay, so that's one thing from the constant, but it turns out we can zero in on that even more. And that's where the back of your investigation paper comes in. All right. So let me explain to you a little bit how you're going to fill out this table if you haven't already. All right, so you're going to take your equation of best fit from Desmos, and you're going to use that equation to fill out your position column here. All right, by basically just plugging in each of these time values into your equation of best fit, and calculating what position your cart would be at that point in time. Okay, so for example, if Desmos gave me the equation of displacement equals 0.5 times time squared, then what I would do here is for this first row here, I would say, what is 0.5 times 0 squared? That's 0. All right, for the second one, I'm plugging in a time of 1 now, so 0.5 times 1 squared. And then the next line, I'm doing 0.5 times 2 squared, and so on and so forth, just plugging in each of these times from the first column into my equation of best fit from Desmos to calculate where I expect my cart to be at these 1 second intervals. Right? So that's item number 1 for you. Once you've calculated your positions at each of these different times, what I want you to do is calculate the incremental change in position by just subtracting 2 adjacent lines. Okay, so what we would see here, for example, is for this first line, see how it's right in between these two, right? So this cell is between the 0.5 and the 0. That's because I want you to subtract these two from each other. So you do 0.5 minus 0 gives you 0.5. All right, for this next one, you do 2 minus 0.5. And for the next one, it'd be 4.5 minus 2, and so on and so forth. You're just subtracting the 2 to see how much your cart moved during that second. Right? So that's our second column here, our change in position per second. And then what we're going to do is repeat that process again for this last column. Okay, so I'm going to look at this column here, and once again, just subtract the 2 adjacent rows here. So I'm going to do 1.5 minus 0.5 gives me 1, or then 2.5 minus 1.5. With 3.5 minus 2.5, and so on and so forth down the column to calculate how much this column has changed each second. All right, so take a moment to finish up those calculations, and once everyone's good to go, we'll go on ahead and unpack really what was going on here and what patterns we found. All right, so hopefully at this point you've filled out those that data table, and hopefully you identified some patterns in there. So let's unpack what exactly we did. I just kind of told you to do some calculations, but I didn't really talk about what they were. All right, so for this column right here, this sort of third column here where it says change in position per second. So you were calculating how far the cart moved during that first second. But then what does that mean? If we're looking at how far a cart moves per second, the change in position per second, we have a special name for that. Discuss with your group. What's the special name for that? The rate at which things are moving, how far they move each second, that's just velocity, folks, all right? That's giving us essentially the speed of our vehicle and direction, but it's always moving in the positive direction, so speed and velocity kind of become equivalent at that point, all right? So what we're calculating then is the instantaneous velocity and how that's changing as our cart is continuing to move along here, okay? So that's what we got here. Change in position per second, we're calculating the velocity. And then for this next column here, we're calculating the change in velocity each second. Now, if we wanted to sort of represent, use a word to describe how much the speed is changing per second, what name might we give that? Discuss with your group. For me, when I think about the rate at which something is speeding up, I like to call that acceleration. All right, so what you've done unknowingly is calculated the acceleration of your cart. That is the value in the far right column. Now, my expectation is that if we did this right, you should have gotten approximately the same value for every single item here in this rightmost column, right? All of your acceleration values should be the same, indicating that your cart maintained a constant acceleration, right? Last thing I want to do with this data table, this is where I get really, really excited, all right, is I want to compare that constant from Desmos that you use to calculate everything, that A value here, with the acceleration that you just got in your data table. Discuss with your group what is the relationship between these two values. What we should find for every group is that your acceleration is double the value of the constant from your best fit line, okay? That constant is equal to 1/2 of the acceleration, which means that our equation of best fit really gives us the formula displacement equals 1/2 of acceleration times time squared. Now, this only works for an object that starts from rest. We'll talk more about that a little bit later in class. But that ultimately is the significance of our equation of best fit and this relationship among displacement, acceleration, and time. Ta-da! You should be very excited about this right now. I can hear you clapping all the way from here. It is very good. If you have questions on this, that's okay. When I get back, we can take some time to unpack it more. But hopefully that gives you a little bit of closure on this investigation and you're ready to start diving into some other things. All right. I love you. I'll see you soon. Bye-bye.